My name is Tatiana Gary and I'm an aerospace major.
My name is Oscar Rodriguez and I'm an aerospace major.
My name is Colin Doyle and I am also an aerospace major.
My name is Robert Troutwine and I'm a mechanical engineer.
My name is Guillermo Villalobos and I'm a mechanical major.
My name is Yvette Williams and I am mechanical engineering.
And this is our NASAMINDS Lunar Dust Mitigation project. So lunar dust plays a major issue for NASA in all of the moon missions, especially now as they go onto their Artemis mission. Back in the 60s with their Apollo missions, the electrostatic dust is very fine and it would stick to spacesuits, important control surfaces. Astronauts would inhale this and it would damage their lungs, so it's a major concern. Our solution, right here, the LRO, or Lunar Regolith Obliterator, uses vibrations and an electrodynamic dust shield to dislodge dust automatically from the solar panel.
The main inspiration for the design of this project came from Kennedy Space Center with their electrodynamic dust shield. They essentially took transparent conducting metals in a parallel pattern with a voltage running through them to create an electric dynamic dust shield or field essentially. This project is different from ours in the case that they were using AC. Our team uses DC to create a more uniform electric field, and then we're going to pair this electric field with these vibrations in order to get the dust moving.
Let's talk about the benefits of our system. For our dust mitigation system, NASAMINDS tasked us with making sure that we could remove 90% of lunar regolith off a solar panel. Another one of our requirements for the competition was making sure that it was autonomous, having minimum interaction between the astronaut and the system. This helps with saving time, effort, and also make sure that the astronauts are not put in any risk or harm's way while they are trying to clean the solar panel. Another one of our requirements was making sure that we wanted to make it scalable, making sure that the system itself was able to be placed on different solar panels or a rover that is on the moon for the next Artemis mission.
For our system concept development, the team initially believed the scope of the project to include making our system lunar rated. However, this changed when factoring our team size, the resources we had available, and the time given. This resulted in us scaling down the scope of the project to a smaller technology demonstration. We had multiple different ways of solving this problem, but through using industrial research and comparing them via trace study tables, the team believed the best way to solve this dust mitigation problem is to use a combination of EDS and ERM motors. These changes result in our final product.
Per NASA's requirement of making the system as autonomous as possible, we introduced a sensor, specifically a Kinect sensor that is capable of detecting dust, particularly a change in depth across the specified surface, in this case the solar panel. The way this sensor works is that as soon as there is any change in depth, as I mentioned before, it will immediately turn on the EDS and ERM subsystems, essentially making it as autonomous as possible.
So using the panel's dimensions, we created a 3D model on SolidWorks. That model was there exported and we imported it to ANSYS, Nastran, and Fusion to conduct modal analysis to get the best vibrational results. The results yielded the first two modes of interest. They occur in 184 Hz and 364 Hz. Since our design is not intended to go ever past 300 Hz, we only want to avoid using running our ERM motors at 184 Hz to prevent those resonant frequencies.
As mentioned earlier, the EDS works on this concept of almost a contactless conveyor belt, where an electric field is generated between two conducting electrodes. In our design, we have our copper conducting electrodes, and a lot of analysis and mathematical testing went into determining the spacing between these electrodes here. Ultimately, a spacing of about 1 millimeter was determined between the copper traces. Additionally, for our ITO capacitor method, we also would put in a lot of mathematical testing to determine the optimal voltage and the spacing in between these capacitor loads in order to move and transport a 50 micrometer dust particle. Ultimately, the distance of 10 millimeters was determined, and the voltage of about 1,000 volts was determined for the ITO capacitor.
To start the walkthrough of our final prototype, we start here at our solar panel. Obviously, energy would come into the solar panel. We also have our battery here, And in the optimal system, our solar panel would be charging our battery through the charge converter, and then our battery feeding into the charge converter would run the rest of the system.
For extra safety precautions, the solar charge converter also acts as a manual off and on switch to toggle the system off and on manually.
So from the solar charge converter, it comes out at 24 volts, and then we send it to a buck converter to step it down to 9 volts for the Arduino. This then powers the Arduino, which is both powering the rest of the system and receiving input from our computer running a MATLAB code, which controls the sensor. When the sensor receives input from the dust falling onto our solar panel, it then allows the code to turn on a few ports in our Arduino to run our two systems. The first system is our vibration system, and the current comes out into another buck converter that steps down 5 volts from the Arduino to 3 volts to run our ERM motors, which are currently attached to the back of the panel, as you can see here. Our next system is our EDS system, where the current comes out of the Arduino once again at a voltage of 5 volts, is stepped up to 16 volt to be used with this larger step-up converter. This larger step-up converter then steps up the voltage to around 800 volts to run our EDS subsystem. This system can be seen right here in the corner of our panel, where dust would be electrically discharged away from the solar panel.
Let's talk about the milestones of our project. One of our goals and objectives for our project was making sure that 90% of the dust was distributed off the solar panel. As you can see in our testing, we were able to successfully remove the dust at an efficient way, making sure that the solar panel was not affected. Let's talk about some of the setbacks that we had in our project. For our original design, we were trying to make sure that we were combining vibrations and EDS together in the most efficient way as possible. But along the way, we stumbled across that some of the small electronics that we had to use for our system were high voltage. We had to create a new way for our system to run, making sure that we had buck converters that would lower the voltage enough to go inside the Arduino, and also making another buck converter that would have a lower voltage that would start the ERM motor. For our EDS system, we had a couple setbacks. We originally wanted to have the Arduino connect to a step-up capacitor that would connect to the ITO capacitors on the solar panel. We later find out through research and testing that 1200 volts is a lot to have the system do. So we had to do some more research. We came up with having a step-up converter that would also reach to another step-up converter that would distribute the amount of voltage that we need to charge the particles and remove them off the solar panel. For our sensor, we were able to originally try to figure out and use a proximity sensor, which would be able to detect the dust. But through further research, we were able that the proximity sensor was not the best fit for us. So we wanted to use a Connect sensor. It was able to detect the change in depth off the solar panel. When the dust is detected on the solar panel, it will start the system and make sure that it is autonomous.
So we have several recommendations for this project. First, for the vibration system, we would recommend larger motors for a larger surface. For the EDS system, we would recommend extending the system across the entire panel. We also recommend testing this via AC current. Also, we would like to see how this performs under vacuum chamber testing and radiation simulations. For the controller electronics, we would like a more sensitive sensor to be able to detect the dust and regolith on a panel. We would like more electrical engineering involvement, as well as a more programmable motherboard and better isolation.
So due to the fact that we were using a lot of electricity, very high voltage, and we were working with some very fine dust particles, we had to take several safety measures. One was the use of insulated gloves during any kind of electrical testing, and the use of goggles for anything when we used our dust. The dust that we've been using is simulated lunar regolith, and it matches the properties of lunar dust, some of those being that it's very jagged, and it would be very, very bad if we inhaled it. So another safety protocol that we used is anytime we were testing with dust or anytime we were testing with electricity, we made sure that we stayed at least a meter away from any live components. Additionally, to protect things like a computer, we had to isolate the USB port and make sure that there is no charge coming back onto the computer to damage the computer or any other components. And we also, to be extra safe, had fire suppression protocols in place, such as having a mandated person with a fire extinguisher, as well as isolating any components that could catch fire due to the high voltage that we were running through them.